Alright, welcome everyone to the live stream. Today we will be basically looking at propositional logic. I will be attempting the tutorial questions in the class and that I'm teaching this semester. And I'll be attempting the tutorials basically from scratch. There were some tutorials I could not finish during the class itself, so I'm going to cover those extra questions today as well. And we'll be doing this basically every Thursday. On some Mondays, I'll also be streaming as well. And that basically would cover all of discrete math, at least the class I'm teaching, at least until the final exam. So we should be able to cover everything up to the final exam when that happens. Alright, so we will look at some of the questions, and in fact, actually we're going to look at all of the questions, and what we will do is also recap some of the ideas in propositional logic, some of the definitions and the results that we can freely use when we want to prove other more complicated materials. So let's look at the first question. The first question says that we will let P and Q be false propositions and R be a true proposition. We need to find the truth values of some propositions. So let's write down the propositions of interest here. The first proposition looks like this: the conjunction of P and Q, all implying R. P precisely when Q or the negation of R. P and this long expression, which we're going to write this way, and the last one, which is even longer, which looks a little bit like this, Q or R, or this expression here, and Q or R. We want to determine whether each of these propositions are true or false. A proposition is a statement that's either true or false, and we know some operations on propositions. So let's look at the first one. So for part A, I'm going to erase all of this first. So for part A, we need to look at whether this proposition is true or false. So the question tells us that P is false and Q is false. So we can make the substitutions. We know that R is true, so let's substitute that. And we are well aware that when we take the conjunction of false and false, we will get false, because that's what it means to have a conjunction. Oops. The conjunction is true only precisely when P and Q are both true, and it's false otherwise. It's a pretty strict operation. So we know that false and false will give us false. But that raises the question on the truth value of the implication. So the implication, for several reasons that I can elaborate in the future, or maybe at the end in the Q&A and whatnot. For reasons that I may or may not have time to explain, the implication is true, or rather it is false if the guy before the arrow is true and the guy after the arrow is false. So if we get a situation of true implies false, we will define P implies Q to be false. Will be true otherwise. Some of us might be concerned with these two situations. If P is false, then why is the outcome still true? It's almost as if you start with the wrong assumptions, you can obtain any conclusion you want, as absurd as it may seem. You can't really use it in the proof, but as a whole, if pigs can fly, then I'll have $1 million by tomorrow. whether it's true or false, this implication is true. We call that a vacuous truth. So in this case, we have a false implies true situation. The answer will be true. Not because of any real validity, but simply because, well, if the assumptions are false, then you can get anything you want, true or false. Okay, the second proposition of interest is this guy. P and Q or not R implies P. And we might want to bring this down just to help us sort of track things. So we now see a few more operations. For example, the negation over there. We have a negation and we have the disjunction. Let's first maybe make sense of what these things are. The disjunction will be true if at least one of them are true, and false if both are false. It's a much more relaxed condition than the conjunction. The negation, as the name suggests, will take a true statement and make it false, because that's the negation. It will take a false statement and turn it true. So we can now attempt to evaluate this proposition by substituting the values. We know that P and Q are both false, or rather we are given that P is false, Q is false, R is true. So let's plug all of those letters in. Let's plug in the trues and the falses in and see what we get. In fact, we're going to get a statement of the form false implies something. Now what's interesting about this is that I may not know what this entire expression is, but a conjunction of false and something, if we look at our truth tables, a conjunction of false and something will always give us a false result. For that purpose, I don't have to do any more calculations. This answer must be false. For the next one, oh, I think that was part C. I got the numbering there wrong. Let's look at part B instead. Part B will be this statement. And we want to show whether that's true or false. Now we have this double arrow. It's called a biconditional. And the biconditional tells us that the two things on, or rather the expressions on the left and on the right have the same truth value. It doesn't tell us which is true or which is false. It just tells us which has the same truth value. What that means is that the truth table of the biconditional is going to be true precisely when the truth values are the same. And it's going to be false otherwise. So we can work out this expression. However, we do have a slight, okay, never mind. However, we do have a slight difficulty with this expression. Do we mean this expression or do we mean this expression? It's kind of annoying because we need to take care of our quantifiers here. However, the convention is that we will take this pair of brackets, or rather this pair of brackets, and we will put a bracket there. And the convention we are using is going to be this hierarchical system of operations. It will be the negation, followed by the connectors, and followed by your arrows, if you would. So in other words, the negations always come first, followed by the conjunction or the disjunction, and finally the implications, be it two-sided or one-sided implications. Let's plug in the values and see what we get. So we are going to get P, which is false. We're going to get Q, which is false, or negation of R. So let's just put negation of R. The negation of a true statement has to be true. and the disjunction of two falses will be false. So we now have a statement, a proposition, stating that the truth values on both sides are the same. For the biconditional, the result is true, because the biconditional tells us that the two guys, or rather the biconditional is true if the two guys have the same truth value. It doesn't matter whether they're true or false, as long as they are the same. Let's look at our last question, which looks this way. Q or R, or the negation of P, there we go, and Q or R. We could try to manipulate some logical properties if we would. However, let's just start from the beginning. Let's just plug in Q, R, P, and see what we get. Let's do it this way. In fact, R is true. So we're going to get Q, or rather we're going to get something, whatever this thing may be, or a true statement, because R is true, or whatever this may be. And we will see why this is useful in just a moment. Q is false, but I'm just going to put it this way, or true, because R is a true proposition. The beautiful thing about ORs is that as long as we have one expression that is true, I think this is called the disjunction law, which we can prove later. As you can see over here, as long as we have one guy that's true, the disjunction will always be true. That's pretty awesome, because we can instantly evaluate these guys to be both trues. And once we evaluate both guys to be trues, the conjunction of two trues is indeed true. Whoops. The conjunction of two trues has to be true. That is how we approach these substitution questions. Of course, we could try to invoke some more powerful weapons later on. So for the next question, we are going to consider this object called a graph. Whatever this means, we don't have to worry too much. We have a bunch of propositions. The first proposition is that the graph G is a tree if and only if it is connected and acyclic. So if and only if G is connected and acyclic. The next statement says that for G to be a tree, let me just write it out in English. In fact, we will slowly work on these propositions one at a time. Our job is to try to rewrite this proposition and the next few propositions symbolically using some letters. So we're going to abbreviate what we're talking about here. C is going to abbreviate G is connected. A is going to abbreviate G is acyclic. And T is going to abbreviate G is a tree. We will need to use symbols to sort of express this idea. So what do we have here? Well, we have G is a tree precisely when G is connected and acyclic. And what it means for G to be connected and acyclic is that G is connected and G is acyclic. So we can actually decompose this to mean G is connected and G is acyclic. And what that tells us is that we can actually use A and C to abbreviate the right hand side. So that is the first one in terms of if and only if. For G to be a tree, it is necessary that G is acyclic. So what that means is that for G to be a tree, for G to be a tree, it is necessary for G necessary for G to be acyclic. That is what it means. And how do we represent this symbolically? For reasons that are a little bit tricky to elaborate on, when we use the phrase "it is necessary for," we usually mean implication. So what does it mean? Well, the idea is that for G to be a tree, it is necessary for G to be acyclic, which means if G is not acyclic, then G cannot be a tree. By doing what we call the contrapositive, for G to be a tree, it is necessary for G to be acyclic. In fact, we can sort of, we can condense it this way. The idea is almost that it is necessary for, meaning that if the outcome doesn't happen, the original guy can't happen. It's a little bit tricky. It's one of those things where whether we get it or not, it's fine. It's a language thing in the math world. I like to say that math people are lazy and crazy. Here we're just not making any sense. Shout out to all our 1, 2, 3 on homies. Sounds about right. Now, being a tree is a sufficient condition for the graph G to be connected. So being a tree is sufficient for G to be connected. Once again, this is one of those strange math world lingo that basically says that once I know that you are a tree, I know you are connected. And that means being a tree implies being connected. So sufficiency basically says that the moment I know you're a tree, I definitely know that you will be connected. If you're not a tree, you could be connected. I'm not saying you are, I'm not saying you aren't. I'm just saying that if you are a tree, I definitely will know that you will be connected. That's the idea of this phrasing. And again, the implications, the arrows are kind of the more important part here rather than the English. It's one of those weird things. In math, we say if and only if. I mean, this phrasing doesn't really exist beyond the math or philosophical world. Let's look at the third question. For our third question, we need to fix a tautology T. So we'll let T denote a tautology. And we'll let C denote a contradiction. We'll let P, Q, and R be propositional variables. And propositional variables basically mean they are placeholders. So P could be true and false, we don't know, but we'll let P represent some truth value. It's something like letting X be a real number, or letting N be an integer. It's just a placeholder. When we combine these placeholders together, we get what we call a compound expression. And there's a little subtlety involved in these ideas here. Compound expression, yes. Now, we need to prove a bunch of logical identities using truth tables. This is arguably the most tedious and yet the most straightforward part of this tutorial. So we're gonna prove some logical identities. First, you want to prove this identity, which basically says that the rainbow method makes sense for logical expressions. So in other words, if you take P and Q, you can do a rainbow method here. We call this the distributivity of this conjunction over disjunction, because in a sense, it sort of goes over into the disjunction. So let me write that down completely. And let's prove this using truth tables. Truth tables. This could take some space. So let's add some space here. I'm going to do it this way. So this is P, Q, and R. I'm going to add some space here because I think we're going to need some I don't want to skimp on space. I think we should use as much space as possible. This compound expression is built up from P and Q. We call this P and Q. P and R. And their disjunction. The OR in a sense. And all we need to do is to check them one by one. Thanks, Brendan. Love it. Love the support. So here are all the different options. What we're doing here is basically checking all the different possibilities of P's, Q's, and R's so that we can exhaust every single possibility of how the compound expression could turn out. It could turn out true, it could turn out false. We don't know. And we aren't too bothered about it as long as we can check every single situation. So let's take a look at that. This basically exhausts all of the different possible options of P, Q, and R being true or false. Let's do the hard work. Now, the conjunction is interesting. The conjunction is true precisely when P and Q, or rather when the constituents are both true, which tells us that these two guys are true. I realize I could use green for true and F for false. I'm gonna do that in the future parts of this tutorial, of the tutorial questions. But the interesting thing here is that everything else has at least one guy who is false. And once you know that there is at least one guy who is false, you know for a fact everything else has got to be false. That's an interesting shortcut. The conjunction is very, very strict on trues and falses. We can do the same thing with P and R. Let's check when it's true and when it's false. It's true in this row, it's true in the third row, and it's false everywhere else because at least one of the other guys has to be false. And finally, we need to check the disjunction. The disjunction is going to be false when both are false and true otherwise. So in every other row, basically the fifth row onwards where both P and Q and P and R both are false, everything else here will be false. Man, that's the way to go. Let's make it colorful. And I have not actually answered the question. If you think about it, I've actually not actually answered the question, and the reason why is because I've only checked the possible truth values for this compound expression. Actually, I have not checked the truth values of this compound expression. That's going to take a little bit more work. So let's do that. We're going to consider Q or R and then the conjunction. So for Q or R, that will be false when both items are false, when the constituents are false, and true otherwise. The disjunction, in a sense, is very relaxed on true, but very stringent on false. So let's do that. Q or R will be false, false. And in every other instance, we have at least one guy who is true. So let's make sure everything else is true. And finally, we need to check the different situations when P and Q or R, when these two columns are true. We can very quickly check that we'll get the first three columns. In every other column for P, it's gonna be false, so we don't even have to bother with any of the remaining four options. And for the fourth row, we get P being true and yet the disjunction being false, so that's false. So apart from the first three rows, everything else is false. And for the first three rows, we will get true. Something beautiful happens here, because if we now compare this collection of truth values, by the way, this corresponds to this compound expression, and we check this collection of truth values, which corresponds to this compound expression, we will see that they correspond. And what that means is these two expressions are indeed logically equivalent to one another. That's slightly long and tedious, but ultimately doable. And part of me actually wants to use Excel to do this, but it's fine. We're just gonna go on. So I think that was actually part 1, but it doesn't matter. I mean, the labeling is not as crucial as the content of the result. We have another result, and this one is slightly more simple. I'll say it's a much simpler result that we can try to establish. We want to show that the conjunction of a propositional variable and itself is equivalent to just itself. Which does make sense, right? I mean, if both the things are true, then obviously. But let's just check this out carefully. We have the proposition P. We have the propositions that we want to build up. And we want to check whether they are true or false. In fact, these are the only propositions we care about. So let's just put a smiley face here. I don't know what to do with the extra space. So P could be true or false. And if P is true, then P conjunction with P will be true conjunction with true. That gives us true. And if P is false, then false conjunction with false will give us false. That gives us false. And we get that the truth values in both columns, this column corresponds to this guy, and this column corresponds to this guy, are both true and false, which means we're good to go. This actually works. They are logically equivalent. It's great. Let's check the next one. The next one is what we call, I think it's called an absorption law. Absorption law. I'm not sure what the name is. I believe it's called the... Wait, let me write down some names. I believe this one here is called the negation. No, it's not negation. I'm not sure what law it is. Idempotence, I think. This is called idempotence. I think this is called idempotence. The idea is sort of if you do the same thing, you're gonna get a similar expression. The maximum number of propositions that a truth table would be useful and efficient. Well, if we have a compound expression involving, say, n variables, then we're going to check completeness, we're gonna have to check every single possibility. That might take a little bit of energy. So I think this is where the power of proofs come in. If we can try to sort of establish these propositions through proofs rather than truth tables, then we might be able to do potentially an infinite amount of work rather than have to check 2 to the n possibilities of the truth table. So in general, if we want a very brute force approach, 2 to the n. But if we have some theorems we can use, that's the way to go. We could probably use induction to extend some ideas. That's possible. So there's that. Okay, where were we? Alright. Okay, so let's do this one. P conjunction with P or Q will give us P. In this situation, we have P being the stricter of the two propositions or compound expressions. So in other words, we sort of take the stricter one. Something like sets and subsets. But let's just use logical tables to establish that. So in this case, because the expressions here involve are just 2, P and Q, we only need 4. 2 to the 2, that's 4. So this can either be true or false. And we simply need to check the different expressions. So we need to check P or Q. And we need to check the conjunction. And then we'll compare this table over here with, well, this column of values over here. For P or Q, that's going to be false when both items are false, and it's going to be true otherwise. And we'll have P and the disjunction, which tells us that we need to compare when these guys are both true, then we'll get the outcome being true, and if at least one of these guys are false, the outcome will be false. In this case, P is gonna be false, so that's gonna happen. And when P is true, P or Q is gonna be true. So there we go. In fact, the two columns do agree with one another. The beautiful thing about establishing these results using truth tables is that we can later totally avoid truth tables to establish future results. And there are a few little tricks up our sleeves that we can do, so stay tuned for that. Finally, we need to show that the negation of a tautology has to be a contradiction. And to do that, let's just check it out. Let's check the definition of a tautology and the definition of a contradiction, and finally the negation of the tautology. A tautology, by definition, is always true. A contradiction, by definition, is always false. And the negation of a tautology is, well, the negation of the true is going to be, well, false. So we do get the same truth values in both columns. Alright, so that we have this column, we have this column, and we have this column. Oh well. And we are good to go. So we do get equivalence over here as well. That was rather long. That was rather tiring. I believe when I was going through this tutorial, I actually skipped this in the lesson. But in this live session, we're going to answer everything. It's gonna take some time, but we're gonna get there. Using the results in A, we could actually try to derive some results in part B. So let's look at the first one. We've already proven that we could rainbow the conjunction into the disjunction. We've already proven this guy. Whoops. I think this is a disjunction. There we go. We could sort of bring the conjunction in already. We want to show, our goal is to prove that we can do the same thing with the disjunction. And our approach to do this, we're going to prove this result. We're going to use this result called De Morgan's law to basically do flipping. Flipping allows us to negate everything, but let's just write out De Morgan's law properly. So De Morgan's law, we're going to use De Morgan's law here. Basically allows us to negate compound expressions. And what do we have? What does the laws state? If you negate a conjunction or you negate a disjunction, you can push in the negation symbol. Oops. You can push in the negation symbol, and whenever the negation encounters a conjunction, it will flip it. And whenever it encounters a disjunction, it will flip that. So that's what's gonna happen when it comes to De Morgan's laws. So we're gonna use De Morgan's laws to help us here. The idea is the fact that P or Q and R could be thought of as the negation of something. Right? It could be thought of as the negation of the negation of P. So we do have a result called I believe the double negation result. Let's just write it here. That tells us that if you do a double negative, you get back the original guy. It's a little bit like real numbers in this result, but that's the idea over here. To use this result, we can now replace each proposition with the double negation. I probably don't need to do everything, but I'll show you which ones I want to use. Basically, I want to go into the reverse direction of this. I want to go from here to here. I want to do that. So what's the catch? The catch is that it's going to be the negation of the negation of P followed by the negation of the negation of the compound expression Q and R. You might be wondering, wait, do I not want to push in the negation to Q and R? I don't want to do too much work at the moment. I just want to slowly deal with the negations one at a time. So I want to go the reverse direction. In a sense, we're sort of factoring the negation. Just like factoring a minus sign almost. So we're sort of factorizing the negation symbol, if you would. That will cause all of the disjunctions to flip yet again. So we're going to get negation of P, conjunction, negation of Q and R. And at this moment, I'm very tempted to use the result that we have shown over here. Well, not this one. I'm very tempted to sort of use the result that we have shown. I'm very tempted to try to use that result. Unfortunately, or rather, sorry, pardon me, I'm very tempted to use this result. However, we don't actually have a result of this form just yet. This is where I'm going to actually push in the negation symbol. Like this. I'm going to push in the negation symbol. Now, if we look carefully, we actually do get a form. Just like the proven case. We can actually rainbow the conjunction into the disjunction. So let's go ahead to do just that. Let's put our goal inside over there. So we're going to rainbow the conjunction over the disjunction. Negation of P and negation of Q, or negation of P and negation of R. And all we need to do is to gradually, one step at a time, push in the negation symbol, and we hope we would obtain the goal that we attained for. Let's copy and paste our goal so that we can celebrate when we get there. So this is our goal. I'm gonna just put it there. Just do that. We want to get there. So let's get there gradually. We need to push in the negation symbol, and that means another round of De Morgans. It's the negation of the first guy, conjunction the negation of the second guy. You might be wondering, are we gonna do infinitely many De Morgans? No, I don't think I have that much energy. But let's just push in and hopefully get everything done. So the first guy is going to be the negation of this compound expression and the negation of this compound expression. Within each of these compound expressions, because that's our hierarchy once again, we're going to push in the negation symbol one more time. And hopefully, we'll get what we want. So we'll get the negation of a conjunction is a disjunction. And we're going to get the negation of the negation of P in the first guy. We're going to get negation of the negation of Q in the second guy. Over here, we're going to get negation of the negation of P. It's getting a bit long and tiring. I admit it's pretty laborious. But we're almost there. We're almost there. And we're negation of the negation of R. In fact, I think this is pretty much the most troublesome one among all of the different expressions. So the negation of the negation of P is a double negation, which means that's P. Or Q, because that's double negation of Q. And then we're going to get double negation on P, that's P. Or a double negation on R. And lo and behold, that is actually the goal that we were hoping to attain. That's pretty much the most laborious of all of the options, and it does get a bit tiring. But thankfully, after this tutorial, we can basically use this result for free. We never have to prove this ever again. That's a beautiful thing about proofs as well. If you do it once and you do it right, you can pretty much clear it all. Now that's the longest one out of the way. For part 2, we want to prove that if we take a disjunction with itself, we get back the original guy. And just like before, we have proven, or rather we can say that this is our goal. We can say this is our goal. We would like to prove this result. And we have already proven that if we take a conjunction with itself, we'll get itself. The trick here once again is to rewrite the disjunction as a conjunction via negations, via double negations and negations. So this is what we're going to do. We're going to write P or P. We're going to replace each of the P's with a double negation. So that will be negation of P, and negation of P. In a sense, we can reverse the De Morgan's law and in that sense factorize the negation symbol. But when we factorize the negation symbol, we have to flip the conjunction. So to get a disjunction. And part of me thinks I messed this up. Part of me thinks I messed it up because I'm not supposed to get something this annoying. Yes, I messed up, and that's because at this moment, from here to here, I've actually not done any conjunctions or disjunctions. This is just a disjunction. So when we remove the negation symbol, we're going to have to flip the disjunction into a conjunction. Whoops. There we go. Now we can use our result that we have proven just now to obtain the negation of P, and that simplifies to P. Much quicker, much more simple than the distributivity one. Distributivity usually takes some effort. For the next result, we're gonna look at this thing. I believe the name here is called disjunction. I genuinely have no idea what these names are, but I do know that they are true. And the intuition here, the idea here is the fact that P and Q is more restrictive than P, right? So it should be equivalent to P. There's our goal. Let's write that down. Our goal. And we have proven that if P is more restrictive, it still works. What's the trick up our sleeves? Once again, we will once again try to write this using double negations and De Morgan's. Essentially, all of these results are the duals via De Morgan's law. So let's go ahead. P or this guy. So let's introduce the double negatives on each of these expressions. Let's introduce the double negatives. Now we can factor the negation symbol so that we're left with negation P, and Q. And over here, the disjunction flips to a conjunction, like this. But we do know a little bit about conjunctions. And yet we gotta be careful because we don't actually have this result completely yet. We want to sort of write it in this manner. Fortunately, we can actually push in this guy. We can actually push that in. So let's go ahead with that. Sort of negation of conjunctions. We push in the negation via De Morgan's law. Now we do have the ingredients to apply our proven result, which is the fact that we have one guy, conjunction with the same guy, disjunction some other random dude. So we can actually apply the result. The result here is going to be negation of P. And once we get a double negation, we can put in the P in the back right there. So that's basically the trick. Finally, let's just look at one last one. The goal is to prove that the negation of a contradiction is a tautology. We've proven that the negation of the tautology is the contradiction. And so, what's our sort of hack, if you would? Well, the negation of the contradiction by our proven result, by the proven result, a contradiction is equivalent to a tautology. Well, it's equivalent to the negation of the tautology. That's what I meant. And we have a double negation here. So, we're done. Alright. Now, the next question is interesting. We've been using the double arrows to denote a two-way implication. In English, we like to say P if and only if Q. So P if and only if Q. So we sort of want this English to make sense with the symbols. That's the key idea here. So we are claiming, and we need to prove this claim, that P precisely when Q is equivalent to P only if Q. It's a math terminology, this means only if. And P if Q, right? So this is if and only if. We just want to make sure that the English that we are giving to these ideas sort of agree with our existing ideas. So let's go ahead to prove them. Part of me thinks I want to just use truth tables because otherwise we actually need to use this thing called the implication law. Now the implication law basically says that, let me just write it down here. The implication law states that we can write P implies Q as negation of P or Q. And even if we could use that, I don't think it's really straightforward because we don't really have a lot of useful results for P if and only if Q. I think we can establish some results there, but it boils down fundamentally to a truth table. So my plan for this question is to just simply use a truth table. So by truth tables. Let's draw our truth tables. And we need to compare the expressions P biconditional with Q, P implication with Q, Q implication with P and the conjunction of these two implications. So let's exhaust all the possibilities and check that the two columns do agree with one another. I wouldn't use truth tables if there's a quicker method, but this is as good as we got. So that's how I decide my proof strategy. Simply, people like to ask me, which proof should I use? My simple answer to them is, whichever proof helps you be lazy and correct. Because math people are lazy and math people are crazy. That's just the reality of life. So, P if and only if Q means that P and Q have the same truth value. And that means we're going to get truths on these rows and falses in the other rows. P implies Q is going to be true, or rather it's going to be false when P is true and Q is false. Whoops. And it's going to be true otherwise. Now Q implies P is going to be false when Q is true and P is false. Alright, so true implies false. So in this case it's over here. And it's gonna be true otherwise. Finally, we need to consider the conjunction of these two columns, which means it has to be true. It can only be true when the both constituents are true. It's false otherwise. And let's check that we do get the same truth values for these columns. I believe there is another method. You could try that if you wish. Might take a little bit more effort, but it's doable. So if you're wondering whether I'm keen on taking breaks, I am. That being said, I did do a 6-hour stream on calculus. You can go check that out. I did 100 questions on this concept called epsilon delta. That was hard. That was hard, so let's just put it that way. So we'll let P, Q, and R be propositional variables. We want to prove this statement is a tautology. We want to prove that this compound expression is a tautology. In other words, it's true all the time. And there are a few ways to do this. We could try to go ahead and use truth tables again. I wouldn't be too against it. I actually wouldn't be too against using truth tables here. Because it does seem that I'm just going to use truth tables. Because, yes, in principle, we could actually use the implication law, which says this. We could use the implication law. However, pardon me. However, it sounds like it's gonna take quite some time. So, because there are only 3 items here, P, Q, and R, I'm just gonna go ahead and use a truth table because we can. So let's go ahead and use our truth tables. There we go. This isn't, it can be tedious, but it is a very straightforward approach. So we're almost there. We're slowly building up our final compound expression. Our goal is to show that the last column is a tautology. We want to show that everything here is gonna be all true. Hopefully. We need to check. So let's write down all the different possibilities. Let's exhaust the truths and the falses for the P's, Q's, and R's. You can get this. And we get falses everywhere else. And now let's just slowly fill in each of the columns. And I think you guys know the implication law, so I'm just gonna complete the table. In the short form video, it's gonna be sped up, so there's that. We have one last column to go. Let's do this right. And I believe we are good to go. Let's check it out. Every expression in this column, let's check these two columns. When the left column is false, we're gonna get truths automatically. And when the left column is true, everything on the right will be true. As we can see right here. So we do get all truths. And we are good to go. So it feels good to get one right. It feels good to get that right. And there is a method in which you can sort of derive everything using logical identities. That takes a lot of time. So again, whichever method is shorter, gets the job done much more quickly, cleanly even, and solve the question. Question 6. We're gonna ask the question, is this guy a tautology? In other words, if P implies Q, do we automatically get Q implies P? Can we go the opposite direction? A usual rule of thumb in mathematics is that if you feel like the result can go the opposite direction, it probably can't. So, in fact, the answer is no, it's not a tautology. We can actually try to devise some truth values to check that. So, let's just draw some truth tables. Once again, because we can do that. We'll get P implies. In fact, I realize we don't really need a truth table. Because all we need to do is to sort of, you know what? Let's not use truth tables. There are some other parts where I've used truth tables. Let's just try to establish that this guy has to be somehow false one way or another. So we want to show that this guy is somehow is gonna be false. Right? We want to show that this is going to be false. We will achieve that outcome when we get a situation of true implies false. Whoops. We will get a situation of that. We want to establish this result for a particular choice of P and Q. In order for that to be the case, we need this expression here. We would like Q implies P, hopefully, to be false, and P implies Q, hopefully, to be true. That way, we're going to get this result, and we're going to get our answer. In fact, if we think about it, we can actually get Q implies P to be false when Q is true, P is false, this will definitely allow Q implies P to be false. That's gonna happen. And if that's the case, we will require that P over here is the same exact P. So it's false implies true. Now, the real question is false implies true true? Well, for an implication, if the first guy is false, then false implies true as a whole is true. Of course, you can't really use it to prove anything, but it's still true. So we do get this result because these truths and actually equals to these guys. And we get our result. So that's sort of the thought process behind this particular proof. Here's how I might prove it a bit more properly now that we have the big picture idea at the back of our heads. So let P be true and Q be false. Then P implies Q, implying Q implies P. Sorry, my apologies there. Let P be false, I meant, and Q be true. Okay. Then P implies Q implies P. Let's substitute the values. We're gonna get false implies true implies false. False implies true evaluates to true. True implies false evaluates to false. Now we're getting a situation of true implies false. Finally, false. So, since there are propositions PQ such that this expression is false, it is not a tautology. Sort of to condense the idea is, in general, logic does not reverse. In general, that's the key idea there. Here's the last question in the main set, but I will look at the extra exercises, so stay tuned for that if you wish. We want to consider this. We want to consider this idea. Let P and Q be compound expressions. In other words, they're constituted of propositional variables. We don't know whether they're true or false, but they are made up of these variables, these placeholders of true and false. We want to show, and we are making a claim, we claim that we get this expression is a tautology precisely when, or if and only if, we get this expression here, right? P being equivalent to Q, and we want to once again recap that P equivalent to Q means that the compound expression for P and the compound expression for Q will always have the same true value when you substitute in the propositional variables. They will always have the same. In a sense, this makes sense. But let's just sort of express it, justify it in a contained way. So let's prove it. So how do we go about proving this expression? Let's check it out. In fact, what I might do is to go in one direction and let's see if the logic goes the other way. We may get it, we may not. So suppose this guy is a tautology. That tells us that no matter what you substitute, any substitution, or pardon me, yes, correct. Any substitution of propositional variables into P and Q. Now is when you plug in truths and falses. In fact, we're going to do it this way. For any substitution, P and Q will always have the same truth value. Now this does not come from, equivalence or whatever. It comes simply from the fact that P, if and only if Q is a tautology, that means they must have the same truth value. And yet that is precisely what it means for P, for P to be equivalent to Q. Literally, that's the definition of what it means when we say that two compound expressions are equivalent to one another. We can write it this way, right? We can write it this way. So let's do that. Oops. We can in fact allow the proof to go two directions. It's a kind of a rare sight for this to be the case. So we do have this situation. P, if and only if Q is a tautology, precisely whenever you substitute your different truths and falses, P and Q will always have the same truth value. But that is precisely the definition of P being equivalent to Q as compound expressions. So that's just a subtlety between if and only if and equivalence. In practice, no one really bothers too much about this, especially when we go into the math part of discrete math. This is a little bit more technical at the logical level, but when it comes to discrete math, it's fine. Let's look at some of the other exercises. So we are going to those. So let's attempt that. I've actually not seen any of these questions before, or at least the extra exercises, so this is fun. We're gonna let P, Q, and R be propositional variables. We're gonna consider this compound expression. Whoops. We're gonna compare these two things. And we are asking the question if these two guys are equivalent. What this tells us is that if P and Q implies R, we are going to get P implies R and Q implies R. So what does that entail for us? Part of me thinks this is going to be... Let me think about this. I genuinely, I feel like someone has asked this question before, but I totally forgot what the solution was. So it's essentially as good as not having not seen this question before. So my brain goes into thinking of, I'm tempted to think it's true, and at the same time it's sort of, I can't really find a very useful proof to get there, and I'm not too sure. So what I might try to do is I might try around a bunch of different truth values, and I can already see something that's going to break this. Because conjunctions are really, really strict, right? But implications are more relaxed. That's sort of the mental idea I have at the back of my head. That implications are more relaxed, but conjunctions are more restrictive. So what I have in mind is that well, in order to show that these two things are not equivalent, at least one of the guys must be false. And if at least one of the guys must be false, we definitely need R we definitely need R to be false. Because if R is true, no one really cares, right? So let's see. Oh. Yeah, if R is true, we don't really have to care too much. So let's let me try this out. Let me try out an expression and let's see what happens. Let's try P equals to true and Q equals to false, R equals to false. I don't think this is gonna get us anywhere. Yeah, this is probably not gonna get us anywhere. So let me try. Alternatively, we could just bash out the truth tables and hope for the best. I mean, that is pretty much the most straightforward approach. Let's just bash out the truth tables and hope for the best. At this rate, honestly, I'm just gonna do that. I'm just gonna bash out the truth tables and see. I don't want to bash out the truth tables and see what we get. I don't want to do that. I kind of wanna. Oh, I think I have an idea. I have an idea here, right? So I think, and this is my conjecture, we're going to use the fact that R is in order to make one of them false. We're gonna try to make R to be false. Right, we're gonna make R to be false, and P and Q. Well, I think I have an idea here. Right, so I'm going to let P be true. I'm going to let Q be false. I'm gonna do it this way. I'm gonna let R be false. I'm gonna let P be true and Q be false. And the idea I have in the back of my mind is I'm gonna try to make a bunch of things. I'm gonna try to make this guy false, and yeah, I'm gonna make this guy true. So that's my mental idea, the intuition, my problem-solving idea. I'm gonna try to find this that breaks, and I think this works. So let's go ahead to establish that. If we make this choice of P being true, Q being false, and R being false, then P implies Q, or P and Q implies R is gonna be true and false implying false, which is gonna be false implying false, and false implying anything is gonna be as a whole true because it's a meaningless statement. On the right hand side, however, we're going to get something interesting. We're going to get P implies R and Q implies R to be P implies R is going to be true implies false. Q implies R is going to be false implies false. So we're going to get a statement of the form false and true. Because false implies false is false and true implies false is false. So yeah, false implies false is true, true implies false is false, which gives us false. And there we have it. These two guys, we found some substitutions such that the two guys don't have the same true values. We're good to go. Feels great. Part of me wants to sort of do a one-way implication one way or another, but I need to check. I need to think about that. But it's okay. That's a question. That's our proof. We've shown that, therefore, they are not equivalent. And the key idea at the back of my mind is that this guy is way more strict than this guy. Right? So that's sort of the key idea. But there's a little bit of guesswork involved in creating the formal proof. So this is my proof. Claim not equivalent. Also, I'm not referring to any answer keys, if you're wondering, so I'm just doing this on the fly and hoping for the best. Hope I don't have to do any corrections later on. That will be awkward and embarrassing. Please raise my corrections if you spot any. Here's the next question. Let's take a look at this one. We want to prove that some expressions are tautologies. So our claim is that this guy is going to be a tautology. And roughly speaking, this is what we call a proof by cases in a situation. If P or Q is true, and we know that P implies R and we know that Q implies R, the whole thing should imply R. That's our idea behind a tautology. We could go ahead using truth tables, but I am going to now finally use the implication law. I think it's about time we did it. Although it's very painful. This looks horrible. I'm gonna use truth tables. I'm not even gonna bother with the manipulations needed in order to derive the results. So we have this guy. We have this guy. We have this guy. we have this guy, and then we have, I'm just gonna abbreviate this to be 1, 2, and 3, okay? We have 1 and 2 and 3 implies R. We're just gonna abbreviate because I'm not gonna write the whole thing. And furthermore, I'm just gonna write down truths, and then I'll fill in the falses later. Alright, so it's gonna be a bit like this. I'll fill in the falses later. So let's just go ahead to fill them up. In fact, we will need to fill up until this column. We have these rows to take care of, but I'm just gonna put truths, right? So later I'll just fill in the falses and fast forward it and all that good stuff. I think I've added too many. I think this is enough. Yep, there we go. Conjunctions. Well, strictly speaking, I think we should do it this way. 1 and 2 and 3 implies R. That might make things a little bit more concise right there. So we can get truths here. And we just need to check the last bit. We actually just need to check. Oh, we're good to go, because whenever it's true, whenever the 1 and 2 and 3 is true, R is always true. Whenever it's false, the implication is vacuously true. And that's our tautology. Great. Is a tautology. And that's that. We have one last question in the extra exercises. I think that basically settles it. And here we go. Let's now try to prove this. We'll let P and Q be compound expressions. We claim that this guy implies this guy. Here's our claim. Let me write that down. And in terms of the proof, we actually can use 1.7. We've already seen what happens when we get equivalences like this. Equivalences tells us that the biconditional will be tautological. So let's go ahead with that idea and work things out. So here's our proof. Suppose P is equivalent to Q, then P precisely when Q is a tautology. Which means that the left and the right will definitely have the same truth value. Then the negations will be a tautology. And I'll quickly sort of justify that, because suppose P is true. In fact, the justification is nothing more than the truth table, so basically there's that. Right, P can either be true or false, so all of that. So when you take negations, you get that the biconditional is a tautology. And that means the negations are equivalent to one another. And that's basically it. That's the last question for this propositional logic. And that's basically the argument for these questions. So sort of starting our discrete math revision journey, if you would, our open session live sessions journey with propositional logic. we'll slowly build up the ideas, right? So, in fact, I think as of this point in time, in terms of classes wise, we are at cardinality. So just a quick overview as to how we learn discrete math here. We start with propositional logic. When we move on to predicate logic, this helps us deal with proofs. And then from predicate logic and proofs, we can talk about sets. We can prove things about sets. In fact, proofs just basically connect to everything. But roughly speaking, here's the idea. So once we have sets, we can now talk about relations. Once we talk about relations, we can talk about a bunch of things called equivalence relations, partial orders, and functions. Following functions, we can discuss cardinality. And surprisingly, with the ideas in functions, we can even talk about counting, which is a very different idea from countability. In fact, what we needed for functions in order to get to cardinality, we needed two things, right? We needed injectivity, we needed surjectivity. These two things will give us bijectivity, which helps us talk about cardinality. And once we have functions, we get counting. That's where we have all of our combinatorial ideas. And we can now talk about graphs, which are a very important topic in applied mathematics, computer science, all that good stuff. And even a more interesting subset of that would be on the idea of trees. And this is sort of the roadmap, if you would, of discrete math. Some modules, to my understanding, will touch a little bit on number theory. But for this iteration, this is it. I will say this though, I might touch a little bit on number theory if there's enough demand for it, so I'll do that. I actually did not study number theory in full detail when I was an undergraduate. I did learn a little bit in the introductory math module, but that's basically for this iteration of discrete math, that's the roadmap. Of course, once you get trees, you can branch out into many ideas in applied mathematics and computer science. So there's that as well. And that's it for today's live session on propositional logic. And yeah, hope to see you guys in the next one. We'll be doing predicate logic, and then we'll go into proofs. If I do this right, we should be able to finish every single tutorial 3 days before the final exam. And with that, see you guys next time.